We're going to talk about one of the most important, yet most overlooked pieces of engineering in the entire modern world, the slab on grade. It's this unseen foundation for pretty much everything in our industrial lives. I mean, just think about it for a sec. Those huge factories that built your car, the giant warehouses that sent you your last package, even the big box stores you shop in, they all have this one thing in common. They are all built on a massive, perfectly flat, and incredibly strong concrete floor. And every single one of them starts right here. I know, it just looks like an unassuming patch of dirt. But the transformation of this ground into a high performance surface, one that can support millions of pounds, well, that's a story of some serious precision and engineering. So that's the big question, isn't it? What does it actually take? Because this is so much more than just, pouring some concrete. It's a multi-stage process where every single step is absolutely critical. So let's break it down. Okay, first things first. Before a single drop of concrete even shows up on site, you have to build the perfect base. This is literally the foundation for the foundation. And if you get this part wrong, the whole thing is built on shaky ground from the start. It really all comes down to two key layers. First, you've got the subgrade. That's the native earth, and it gets compacted until it's practically immovable. Then, on top of that, you get the subbase, a thick layer of crushed stone or gravel. Now, this layer is crucial. It's what evenly spreads out the insane weight of the slab and everything on it. And that's what prevents sinking and cracking for years and years. And the prep work is meticulous. The site is totally cleared, graded to exact levels. The subbase gets laid down and compacted layer by layer. And here's a critical part. Third-party engineers come in and perform tests to guarantee that base won't move an inch. These aren't just suggestions. They are non-negotiable requirements for a solid footing that's going to last for decades. So, with the base perfected, it's time to talk about the main ingredient. And look, concrete is not a one size fits all product. For an industrial slab, it's a high performance recipe, a precise formula that's engineered specifically for strength and durability. And what's so cool about this is how it breaks down the science behind it. Nominal strength. That's its raw power to resist getting crushed by heavy machinery. Then there's the slump, which is basically a measure of its consistency. If it's too wet, it gets weak, too dry, and it's impossible to work with. And the cement content? Well, that's all about having enough of the glue to make sure the chemical reaction is powerful and durable. All right, with the base prepared and the recipe confirmed, it is time for the main event. This is a high stakes, time sensitive operation that really demands flawless coordination. But hang on, before the concrete trucks roll in, this steel skeleton gets laid out. This grid of rebar or mesh is absolutely essential. And here's why. Concrete is incredibly strong in compression. It loves to be squeezed, but it hates being stretched or bent. This steel reinforcement gives it the tensile strength it's missing, which stops it from cracking under heavy loads. The pour itself is like a carefully choreographed dance against the clock. Concrete is pumped in, and immediately a power screed vibrates across the top to level it all out. Next, finishers with these huge bull floats smooth the surface, pushing the heavy stuff just below. And finally, as the concrete starts to set, they get on these ride-on power trowels. They kind of look like helicopters gliding on the surface to create that perfectly smooth, dense, and incredibly hard finish. Now, you might think once the surface is smooth, the job is done, right? Well, actually, one of the most important phases is just beginning, and it's all about patience. Yeah, this quote says it all. The work of the finishers might be over, but the work of the concrete itself, that has just begun. This is where the real strength is born. This phase is called curing, and it's so important to understand this is not about drying out. It's a chemical reaction called hydration. Down at a microscopic level, cement particles and water are bonding together, growing these interlocking crystals that create immense strength. And for that reaction to complete, the concrete has to stay moist. So, the crucial point is for at least 5 days, that slab is kept wet, often covered with plastic sheeting just to trap the moisture. I know, it sounds totally counterintuitive to add water to something you want to get hard, but drying out too quickly is the enemy. This slow, moist cure is what lets the concrete reach its full engineered strength. All right, let's move on to the final challenge and address the elephant in the room for any concrete structure: cracks. This is a fantastic question. And the reality is, concrete is going to crack. It's just an unavoidable property of the material. So the goal of great engineering isn't to prevent cracks entirely, but to control exactly where and how they happen. So, why does it crack? Well, it happens for a few key reasons. As the concrete cures, it hardens and shrinks. The surface can also dry out faster than the core, which creates internal stress. And just like any material, it expands when it's hot and contracts when it's cold. All of this movement creates tension. And when that tension builds up, the concrete cracks to relieve it. And a single uncontrolled rogue crack is a huge problem. It can travel in any direction, creating a weak point, a safety hazard, and an open door for moisture that will just destroy the slab over time. It basically compromises the entire system. And this, right here, is how engineers tame those cracks. It's brilliant. They use two main types of joints. You have isolation joints, which act like buffer zones, separating the slab from walls or columns so they can all move on their own. But the control joints, that's the real genius. They are grooves cut into the slab to create a weakened plane. It's like a perforation on a piece of paper. It tells the concrete, hey, if you're going to crack, you're going to crack right here in this perfectly straight line. So, the crucial thing to get is that these saw cuts aren't random at all. They're laid out in a carefully calculated grid, usually every 3 to 4 meters. This grid channels all those natural shrinkage forces into predictable, harmless lines, which preserves the integrity of the whole floor. So the next time you walk across one of these vast, smooth floors, just realize you're not on some simple surface. You are on the final result of a process where every single step, from compacting the earth, to the concrete recipe, to the curing, to the placement of every single joint, is a deliberate, engineered solution to a potential problem. It's this unseen engineering, this absolute mastery of materials and forces that literally supports our modern world. And it really makes you wonder, doesn't it? What other complex, critical systems are hiding in plain sight? Systems that we all rely on every single day without even a second thought.